Okay, welcome back. This is the fourth video for Advanced Mechanical Principles, and we're starting outcome 4 today. Simple harmonic motion. This outcome is relatively quick, relatively straightforward. We're going to look at the first part of the assignment today, and we're going to look at the second part of the assignment next week. Your task for the week effectively is to complete section 1 of the assignment. Simple harmonic motion. What is it? Well, basically it's a movement where the returning force is exactly the same magnitude as the driving force. So in essence, what we get is a sinusoidal motion. So we get something that looks like that with our motion. Okay. Typically this sine wave you will have seen in electrical with AC. So AC current is a form of simple harmonic motion, but this is also how a spring rebounds. Now on Earth we'll never get this perfect sinusoidal motion with a spring because air causes resistance. So what we'll have is a decaying sinusoid, which is effectively heading into the control systems and things like that. For those of you who are going to be working through with this, what we're going to do with this system is we're going to look at the cam follower. Fairly common mechanical application. And for today's session, all we're going to need is a calculator. You must set your calculator into radian mode, which is typically you press shift, you press mode, and you press 4. And to get it back into degrees mode, you press shift, mode, and 3. Some of the more technical ones, like this Casio one that I've got a picture of, it is a little bit more in depth using menus, but I'm sure you'll be able to work it out. Just before we start the example, you may have received the email as well that said I've set up a website designed to store everything on there, so you've just got one place to go to. I'll show you that now. Please forgive the rugged nature of it. I've kind of thrown it together quite quickly just to make sure we have something to do. Okay, so on that website, this should be what you see when you log in, my gorgeous visage there, and you want to go to courses, click BTEC Nationals, and you'll see Unit 14 there. Click Unit 14 and you'll see the 5 assignments in the white buttons, and then alongside the assignments are the videos I've made so far, and this will populate as the videos become available as I record them. Okay, so anytime if you go to this website, where you can't actually see the website address, I've got it linked. It is I shall write it down momentarily. I'll write it on the PowerPoint as we're doing the example. You should always be able to go to that website. It's also at the bottom of the emails I send out to people now. Okay, so that's good. Let's go back and start looking at what we're going to do. So we're going to look at an example system, and hopefully you should be able to see how this is not an overly complicated system. Right, so just at the top of this right now, I'm going to give you this. So the address, if you're after, for that website is sod off Baldrick. I know, I'm sorry, but when I created the name and the address, I never thought I would be creating a professional website with it at wixsite.com /JCB Academy, and that will take you to the main route. I'll also, having just found the option, baldrick.wixsite.com/JCB Academy. And what I will endeavour to do is make sure that that address is always available for on the stuff we do. So let's just clear that back in. Okay. And so this is where you can find all of these videos and all of that stuff. Right. So let's explain the CAM follower. Free study is again amazing. It has a lot of the in-depth explanation of how this works. We're simplifying this clearly for the online side to try and save you time. This CAM has a maximum displacement which is set by this larger diameter here, and we have a minimum displacement which is set by the smaller side. Somewhere in the middle of that we've got what's called the mean position, and that relates to the 0 on our graph. So the mean position is typically set halfway distance of the maximum throw of the CAM, for want of a better word. Because it's sinusoidal, we have a sine in the equation, and x is the displacement set by this CAM. This CAM is in millimeters in this example to make stuff effective. Okay, now the first thing you guys are asked to do is work out what the periodic time is. Now if you look at this, the periodic time I'm showing you on a graph here just to help the explanation. It's the time taken to go from one point of the graph to the same point of the graph, because this then repeats itself, and that's why I've left a little bit of the trace on to show that it carries on. It just repeats itself. It's what we call a periodic waveform. Okay. The time taken to do one period, you can see from this graph, is 0.01 seconds. Okay, that is related to this 200 pi here, because that 200 pi there is effectively omega, which we know from the previous stuff we've done. Omega is our angular velocity. So our angular velocity for this CAM is 200 pi. Okay. Now we can link angular velocity to frequency in hertz, so that is rads per second. Always put your units in. We can convert rads to seconds to hertz by changing a radian into a cycle, and a cycle is one complete period. Now there are 2 pi radians in one complete period, so all we have to do to get the frequency in hertz is divide omega by 2 pi. So our frequency is 100 hertz in this example. But that's not what I asked it. I asked for the periodic time. So how is frequency and periodic time related? Well, frequency is the number of cycles in 1 second. So if we know what the frequency is, it's 1 divided by the periodic time. What that means is that the periodic time is 1 divided by the frequency. So it's 1 over 100 in our case, which is 0.01 seconds. Which I hear you all say, yes, but we already knew that, Andy, because we can see it on the graph. Well, the whole point of this is, let's save us doing the graph. We can work that out fairly quickly just by plugging the numbers in. Okay, so are we happy there so far? Now we move on to the next part of the task, and the next part of the task is to work out the displacement, velocity, and acceleration of our follower at a certain time. Okay, so I'm going to pick a time for this example. I'm going to pick a time of 4 milliseconds. We can see 4 milliseconds here on our graph. So we can see that at 4 milliseconds, our displacement should be somewhere between 20 and 30 millimeters. Okay, so I'm going to go onto a blank sheet now, just so we can do the sum. Okay, and what I'm going to do again is put that web address back up at the top, just so you can see it. I'll make it a header on the future PowerPoints, and that was excellent. So let's come back in. We know that X is equal to 40 sine 200 pi t, and I'm suggesting we're going to use t is equal to 4 milliseconds. So the first part of this task is as easy as it looks. That X is equal to 40 times sine of 200 times pi times 0.004. Please remember 4 milliseconds is 0.004 seconds. And if you type that in your calculator, if you are in radians mode, you will get 23.5 millimeters, which is what we were hoping to get when we looked at the graph just a few seconds ago. So I'm happy with that. When I'm happy with that, I underline my answer. So that's our displacement. Okay. Now, how do we work out the velocity of the cam, or of the follower? Sorry. Well, velocity is rate of change of distance. Okay. So the velocity is equal to the differential of the distance x with respect to the time. Okay, so what we need to do with this is we need to be looking and saying, okay, I need to differentiate 40 sine 200 pi t. Okay, now I have a feeling that this text is all going to disappear in a moment, because I'm about to share with you a table of standard differentials. Okay, so I can rewrite that, but let's share this at present. So as you can see, here's our table of standard differentials. I'll zoom it in slightly. Okay, table of derivatives. We're looking for sine AX, or sine KX as it is in this example. And if we look, the differential of sine kx is k times cosine kx. In our example, x changes to t. Anything multiplied by that t is k. So in our example, we have 40. Can't write on that bit, sorry. In our example, we have 40 sine 200 pi t. Our differential will be 40 times 200 pi times cos of 200 pi t. So I'm going to come back and we're going to write that. Okay, so x we started with x being equal to 40 sine 200 pi t. The differential of x with respect to time is equal to the velocity. And remember, t is still 4 milliseconds in this example. And the differential of that is k. So this 200 pi is my k. K times 40 times cos of 200 pi t. So we're going to get 40 times 200 pi times cos of 200 pi t is our velocity. And then we can plug our t into that. So 40 times 200 is 8,000 pi times cos of 200 pi times 0.004. Tap that in your calculator. Again, you should still be in radians mode, so everything should be okay. 8,000 pi cos. And we get a velocity of minus 20,332.8 millimeters per second, which seems like an enormously fast speed. It's 20 meters per second, basically. Okay, still fast, but that cam is spinning relatively quickly. We have a frequency of 50 hertz, remember. Okay, now to finish this off, we've got the same problem. Okay, so we need to remember this equation for v. Work down. I'm going to lose the screen again because I need to share with you this tab again. Okay, we need to differentiate that again because acceleration is the rate of change of velocity because it's in meters per second per second. Okay, so now we want to differentiate cos of something times x, which is there on our table, and that is minus k sine kx. So these numbers are going to start getting silly, but that is the nature of this problem. The acceleration is enormous. the velocity is enormous. I should actually, as we come back into this, as we come back to the blank screen, I should add a negative velocity can be correct, because it just means it's going down rather than up, okay? Or up rather than down, yeah, or left rather than right. So depending on how we've set our which direction we've set to be positive, we can have a negative velocity, so we're not too worried about that. So V was equal to 8,000 pi cos 200 pi t. And you might notice that in essence all we're really doing is working out what the sine is and multiplying by what's times in by t. So the acceleration is the rate of change of velocity, or you will sometimes see it written as the second derivative of displacement. Okay. Now, if you want to be clever, you can always insult someone by calling them the third differential of displacement, which is the rate of change of acceleration. And look that up and you can work out why I always think it's quite funny. Okay, so 200 times 8,000 is 16 and 5 zeros, which is 1.6 million pi. Oh, sorry, minus 1.6 million pi sine 200 pi t. And t still is 0.004 seconds. So plug that in. 1.6 times 10 to the 6 times pi times sine of 200 pi times 0.004 gives us an acceleration of 2.95 times 10 to the power of 6 millimeters per second squared. And that is our final answer for that problem. Okay, so while the task looks quite complicated and the numbers can become quite huge, it's a relatively straightforward problem to do. I will see you again next week where we'll do the second part of this, which is a spring damper system, and we might look at it's not even a spring, but it's a mass spring system, sorry, and we might look at a pendulum as well. Okay, thank you for joining me. I'll see you then.